When we want to solve a radical equation that contains only one radical, we are going to follow the process that you see here. We're going to begin by isolating the radical. We'll undo the radical using an inverse operation. We'll solve the resulting equation and then check for possible extraneous solutions. So let's try a few. Our first example is going to be the square root of 3x plus 1 plus 6 is equal to 10. Our first step is to isolate the radical, so we begin by subtracting 6 from both sides. And now on the left-hand side of the equation, we only have the square root of 3x plus 1, and on the right-hand side, we have just that 4. Knowing that the inverse operation of the square root is the square, we then transition into squaring both sides of this equation. Squaring the left-hand side, multiplying the square root of 3x plus 1 by itself, leaves us with just 3x plus 1. Squaring 4 gives us 16. Subtracting 1 and dividing by 3, solving this linear equation, we're left with x is equal to 5. In a normal circumstance, this would be our equation and we were done. But because of the squaring relationship, the squaring's relationship with the square root, and the fact that squaring both sides of the equation can introduce an extraneous solution, we want to check to make sure that this answer actually works. So over here, we're going to check our work, and we're going to do that by substituting 5 in where the x is. So we have 3 times 5 plus 1 plus 6. 3 times 5 is 15 plus 1 is 16. Square root of 16 is 4 plus 6 is equal to 10, and that checks out. So the squaring process did not introduce any extraneous solutions. We know our work here is good, and we have our one solution, x is equal to 5. Let's try another. In this example, we're going to use the cube root of 2x cubed minus 1 is equal to x. Still only one radical, and we want to begin by isolating it. Well, fortunately for us, it's already isolated. This radical over here on the left is already by itself. So we're going to get rid of the cube root by cubing. We cube the left-hand side, and we cube the right-hand side. The cube on the left-hand side will get rid of the cube root, leaving us with just the radicand, 2x cubed minus 1. Cubing the right-hand side gives us x cubed. Subtracting x cubed from both sides gives us x cubed minus 1 is equal to 0. Now you could go through the trouble of using a difference of cubes to factor. You're already set equal to 0, try to solve each one of those equations. But this is a relatively simple cubic equation. We just have x cubed is equal to 1. And what's our only solution for x cubed is equal to 1? Well, that's x is equal to 1. We would have got the same thing had we gone through all of the trouble of factoring, but we didn't necessarily need to here. We could solve in a different way. Let's check to make sure that that solution is good. We're going to come over here. We're going to check our work. We're going to start with our cube root of 2 times 1 to the third power minus 1. Cube root of 2 times 1 to the third power is just 2. Cube root of 1, which is 1, which is what the other side would have been, and we get a good solution. Cubing both sides of the cubing both sides of the radical equation did not introduce any extraneous solutions. Our one answer is x is equal to 1. For a final example, let's take a look at what happens when we do have an extraneous solution. Our equation here is going to be the fourth root of 4x minus 13 is equal to negative 15. Again, our first step should be to isolate the radical. We add 13 over. And this is the part where we would stop. We could potentially stop. If you look carefully at this equation, you are taking an even root, an even indexed root of an expression, and you are getting a negative solution. Right now, we could be able to stop and say that there is no solution to this. Because we take an even indexed root of an expression, we anticipate that the answer would be positive, not negative. If you don't catch that, however, it is still possible to try to solve this, and you'll see the extraneous solution. So let's go back to our equation. And pretend that we don't see the even indexed root that can equal a negative, and let's raise both sides to the fourth power. That leaves us with 4x on the left and negative 2 to the fourth power, which is 16 on the right. Divide both sides by 4, and we get x is equal to 4. That's our indication that if there was a solution, it would be x is equal to 4. Well, let's check our work. The fourth root of 4 times 4 minus 13. The fourth root of 16 minus 13. The fourth root of 16 is 2. Minus 13 is negative 11, and that is not negative 15. This is not a solution, and in fact, it is extraneous. That happened because of what was going on right here. Now, that is not to say that every extraneous solution is going to have a spot where the radical doesn't exist. That's not to say that. There are going to be more discrete ones that you're not going to notice as easily, that are going to slip by you. And that's the case. That's why we have to make sure we check our answers at the end. But rest assured, if you do have one where you do realize that it does not have a solution, you are welcome to stop and say that even indexed root cannot equal negative 2, and you could stop. But if you continued the work, you still see that extraneous solution. So just to recap, let's remember our process. We're isolating the radical, we're undoing the radical, we're solving our resulting equation, and then we're making sure that we check for any extraneous solutions. Sometimes the isolating the radical might consist of one move, subtracting 6 in this case. Sometimes you won't need to, and the radical will already be by itself, and you can just jump right into undoing the root that is there. But just make sure you're still checking for those extraneous solutions when you're done, because even in those situations that feel like you solved them correctly, the possibility exists that this work, this line, this step right here where you cubed or you squared both sides could introduce an extra solution.